Okay, with pleasure,
Yes,
I introduce Yutaro Kabata. He's from Kobe University, and he talked about classification of jet of ruled surface and projective in space.
Thank you so much. My voice is okay with this? Or should I use mic? Okay? Okay. Let me do like this. Okay, and first, let me thank to the organizer. Mexico is very nice than I expected. More and more, yeah. And Federico, happy birthday. Yeah, I'm very happy to be here and celebrate you. Yeah. Okay, let's begin with my talk. Today, I will talk about ruled surfaces and generic geometry of it. But today, I don't remove the point with non-immersive point. So, but if we consider some projection, then some degenerate singularities appear even for generic rulings. So, これか。あれ? So, let me begin with introduction. Today, we deal with normal forms of Monge forms of surfaces in projective 3 space. So, and I will deal with real projective space, okay? Then, so Monge forms can be taken as in the following. So, take an affine chart of projective space as R3 with this coordinate. And so, since we consider local geometry of surface, this is okay. And consider that the origin of R3 is a point we are considering. We are considering of its surface jam. Okay? Then the pjet of a Monge form of surface M at the origin is written like this. Okay? So let me quickly review about the surfaces, general surface. So non-ruled surface. The jet of Monge forms for generic cases were classified by Platonova. And maybe George told you the expansion for generic or generic 1 or 2 parameter families of surfaces are given in our work with George and Toru Omoto. So this kind of normal forms are very useful for calculation. And each type in this list can be characterized by contact of surfaces with lines. So especially tangency with respect to parabolic and flecknodal curve is given by Landis. And if we take projection of surfaces, then there appear map jams from plane to plane, and it's A-type. So I mean A-type by the equivalence class with A equivalence. So it's A-type measured in some sense contact with lines. So this classification was done by Arnold and Platonova. And here, but maybe you know well with flecknodal curve, but let me explain briefly. So here, a hyperbolic point is called a flecknode point. If an asymptotic line has a contact of more than third order. And a Fleck-nodal curve is the closure of the set of Fleck-nodal points. Okay. So this is a kind of model picture for generic surfaces stratified by tangencies respectively. Okay, like sombrero, as yesterday's talk. So, okay. Then, so let's consider today's main object, ruled surface. So here, a ruled surface RF in projective space is defined as image of this mapping F. And this mapping is like this. So, これ使えるのか。そっか。We take two smooth curves, x1, x0, x1, and then, and of course, parameterized by the same coordinate. And for each fixed parameter u, we can take a line which goes through both. And this one is actually the image of this, and we call this as ruling. Is the size okay? Okay. And so, then it is classically known by Wilczynski. He's a mathematician of German of the beginning of 19th century. Oh, sorry, 20th century. Yeah. In his book, this kind of Monge forms, normal forms of Monge forms by projective transformation is given for most non-degenerate point. I put these normal forms of the most non-degenerate forms in the previous list of general surface for comparing. So since we have string restriction of ruled surface, there are big gaps for each terms. And this is the Wilczynski's book. Okay. So today I will talk about generic geometry of ruled surface. So this work is joint work with George and Toru. So and first I will talk about classification of 5 jets of Monge forms of ruled surface, and this is actually the main result. And then, based on the Monge form, normal forms, we studied geometry of tangency. First, we analyze Fleck-nodal curve, especially Fleck-nodal curve, and then consider A5 type of central projection. Okay? And this is main part of today. And then I will talk about this. So actually, since this work is joint work, so there are several motivations for each author. So here, let me talk about my motivation. And in my sense, this way is rather very near to Platonova's way, and less easy to understand the geometry of ruling itself. So to consider such kind, now I am revisiting Wilczynski's classical work. So especially this classical book. And trying to connect some singularity theory I have been studying. Okay? So this is today's content. So let's begin with main part. So actually, this is the classification of generic ruled surfaces. Here we gave some stratification and gave the simplest normal form up to 5jet to them. And here alpha beta modular parameters. Okay, later I will show some sketch of proof for this, but it is perhaps not so. It is perhaps a little bit boring. So let me let me show picture with geometry for each case. Okay? これでいいのか。Okay. But before that, let me remark something. So first thing is that any ruling is asymptotic for any point on the ruling for the ruled surface. So there are no elliptic points on ruled surface. So there are just hyperbolic points or parabolic point with multiple asymptotic line, or flat ambiguous point where all tangent lines are asymptotic. And thus, in this talk, for a hyperbolic point, when I say asymptotic line, just asymptotic line, it means the asymptotic line which is not the ruling. And Fleck-nodal curve is also, the word Fleck-nodal point or Fleck-nodal curve is also used in this sense. Okay? And let me add some remarks as extra. In fact, we dealt with also surface jumps of ruled surface which appear for generic one-parameter families of rulings. And in the above classification, as I mentioned before, non-immersive case, So singularity of ruled surface is removed. And the singularities of ruled surface are dealt with these literatures. Yeah. So let's begin with drawing a picture. So first case is with, there are actually, I show you 3 kinds of generic ruling. So first ruling is non-degenerate ruling. Second one is multiple Fleck node ruling. Third one is total ruling. So let's begin with non-degenerate ruling. So this is the most general case. So in this non-degenerate ruling, most points are type of gamma 3 0, but there are 2 distinct Fleck nodal points. And in that Fleck node point, gamma 4 1 appear. And Fleck nodal curve goes transverse to the ruling. Okay? And actually, there are some special points whose asymptotic line has more than fixed order contact. In that point, gamma 4 2 appear. So this is a picture for generic ruling, non-degenerate ruling. Then, then another picture is multiple Fleck node ruling. So for this ruling, these distinct Fleck node points come to a unique point. Gamma 5 2. And the Fleck nodal curve is tangent to this ruling. Okay, this is a degenerate case. And then, so next one is total ruling. General points on this ruling are parabolic point, and its type is gamma 2 1 in our classification list. And while there are some distinct point of flat analytic of type gamma Q22 we call. And yes, and since at the parabolic point, the ruling itself is also a parabolic curve and Fleck nodal curve. So for gamma to 1 general point on the ruling, there are no frequenodal curve outside. On the other hand, there is a frequenodal curve which transverse to the ruling at this flat umbilic point. So, yes. Actually, on this point, there is parabolic and double frequenodal curve. Okay? So, this is the old picture. I have time. Okay, 20 minutes have passed. Okay. And so, okay. And let's compare with the case of general surface. So, in the region of hyperbolic points, all things looks the same. So, yeah, except for this bifrequenode point. But instead of this bifrequenode point, there is this kind of special degeneracy in hyperbolic region. And with respect to the Godron or cusp of Gauss, this instead of that in ruled surface, this frequenodal, this gamma Q22 as a flat umbilic point appear. Okay, then okay, this is a picture and analysis of frequenodal curve. Actually, we calculated frequenodal curve with concrete calculation using computer, Mathematica or Maple or something. Then we get explicit equation for each frequenodal curve. Also for types in generic one parameter family. Yeah. So yeah, actually it takes a little bit time, of course. Yeah. Okay. Then let me show you some sketch of the proof for the classification. Just a rough sketch. So as I mentioned in the previous, by taking a affine coordinate of real projective space, a ruled surface is locally parameterized by this form. Here, X and E are mappings from open interval to R3. On the other, while the mapping E, the curve E is non-zero vector. So here, in this coordinate, X is still this curve, and we can take E as a direction. So in R3, ruled surface is parameterized like this. And then let J be the 5-jet space of map jumps of this type at the origin of I prime. And actually, what we did is an invariant stratification of J for the ruling, or J times R this means the J with the parameter for the rule. So, yeah, like this picture, for on the same ruling, there can appear different kind of frequenodal surface. So this stratification also should be considered. And to each strata, to this stratification, we gave a suitable normal form up to projective transformations. So let me show some example with non-degenerate case with points of only hyperbolic. We can suppose, with this condition, we can suppose that x and e are locally expressed like this Taylor expansion, and then this mapping can be expressed by taking coordinates or something. We will get this form. And here, the coefficients of Aij, of course, depends on these coefficients, KLMN, and of course T0. Sorry, I forgot to say. So this is a Taylor expansion of ruled surfaces at the point T0. So if you take Taylor expansion at 0 T0 for this parameterization, then by coordinate changes, we can get this Taylor expansion of Monge form. So, yeah, and this Aij depends on LMN and T0. So then we can consider the 5-jet space as a space of these, and J times R is the space of these. So with this form, we consider projective transformation to it and eliminate some terms of this from lower degree to higher degree up to projective transformation. Yeah. This gives invariant stratification and also simple normal forms. Like this. Okay? Of course, to eliminate terms, it needs a lot of computations for finding for constructing a suitable transformation of projective space. So, yeah, actually, this took a lot of time. Okay. Okay. Then let me consider also the central projection of ruled surface. So let me briefly remind you of central projection. For surface M, let iota be an embedding, smooth embedding to RP3, and take a viewpoint P in RP3, which is not on the surface Then central projection, then define canonical projection, which associate each point x to the line which goes through x and p. Then central projection of surface is its restriction of this canonical projection pi p to the surface. Then that is a plane-to-plane mapping locally. And this is, in some sense, classification of A5 types of central projections of generic ruled surfaces. So I put here each type in our list of ruled surface, and this is types of central projection with the viewpoint on the ruling. So since we put viewpoint on the ruling, there appear very degenerate types. I have 10 minutes?
5 minutes. 10 minutes.
Oh, 10 minutes. Okay. And this is a type of projection from other asymptotic lines. So for hyperbolic types, they are the same as the case of general surface. And here, since ruling itself is also asymptotic, so there appear so there are no other asymptotic lines. And here, so this is the projection from the ruling, but with the position of a viewpoint on the ruling, there are distinct points for this ruling, and there appeared some degenerate types. And this is a case of flat umbilic. So remember that for flat umbilic, the ruling itself is both frequenodal and parabolic. But there is one special direction from which we see this curve type. So, and actually, the frequenodal curve here we considered is tangent to this special direction. So this is things which I explained to you. Yeah. Okay. Yeah. 8 minutes. So one interesting point is that actually the difference for this type and this type did never appear with the characterization with respect to Fleck-Nodal curve. But if we take central projection, then the difference of singularities at distinct points are different. So these new points can be found by taking central projection. This kind of things also happened in the case of general surface. Okay? So, yeah, even in general, it is interesting that even for, so there happened similar things between the ruled surface, generic geometry of ruled surface and general surface. Okay, this is the analysis of main part. Okay, 5 minutes. And then let me show you, let me talk about this topic. So Wilczynski's classical work and my future plan. So let me begin with my motivation. Why I am studying ruled surfaces. So first, I want to understand geometrical meaning of map jams, A class of map jams with high codimension, like this type. So this is a plane-to-plane map jam. And if we have this kind of Taylor expansion with this 5-jet, then this complicated condition distinguish this butterfly type and the degenerate type of butterfly. These are different A type. But we have condition, but we don't have any good geometric characterization. I want to know about this. And the second thing is that I want to know how the difference of A types appears in some concrete geometrical setting. So in the case of central projection of surface, so at the degenerate hyperbolic point, the previous equation, so, sorry. Yeah, this equation gives us a quadratic equation with respect to parameter A. Here, parameter A is a parameter of the position at the asymptotic lines of the surface. And A, B, C depends on coefficients of Taylor expansion of surface jumps. And so this defines or determines two distinct points. And from these two distinct points, this degenerate type appear, while from other point, this usual butterfly appear. But these terms are also so complicated. So also for this, we cannot understand the geometrical meaning for the surface so far. So I thought that if we studied ruled surface, things would be more easier to consider. And actually, in Wilczynski's work, he associates study of ruled surface to study of this differential system of differential equations. And actually, this can be reduced by coordinate change and the change of x and y with this form. The first primes were eliminated. And with this form, the ruled surface is, when we consider the ruled surface in the similar situation with the previous setting, then the quadratic equation here, the coefficient ABC depends only on the value of P at 0 and some coefficient of Q in this normal form. So, so far, of course, I've never gotten any geometric characterization, but this form for ruled surface looks easier to interpret. So, so this is future plan. So expanding Wilczynski's framework to also degenerate rulings like those. He never characterized those. And then, and of course, understanding geometry of A types appearing in central projections. And based on this, I hope that I will get a hint to characterize geometry of A types of map jams. This is all. Thank you so much. Federico, happy birthday again. おめでとうございます。
Questions, comments?
Maybe no. No. Let's go to questions.
Thank you, Yutaro, again. Break.